going to learn about crystal field theory of coordination compounds. First of all, what is the main use or main advantage of crystal field theory? Crystal field theory explains the colored property of the coordination compounds. Generally, the color property is produced for the involvement of DD transitions. For example, so two types of complexes are there. One of the complexes is tetrahedral complex, and another one is octahedral complex. So first of all, what is the meaning of octahedral complex? Octahedral complex, first I am going to discuss octahedral complex. Octahedral complex means the given coordination compound containing 6 ligands. The type of complexes are known as octahedral complexes. For example, one of the octahedral complex is taken K4FeCN6. This is one of the important octahedral complex. The iron coordinated with 6 cyanide ligands. This is potassium hexacyanoferrate 2. This is the IUPAC name of this coordination compound. So the cyanide ion is a strong field ligand. Last class I discussed ligands are subdivided into two categories on the basis of field strength. One of the categories is strong field ligand. Strong field ligand. Strong field ligand, some of the examples are NH3, CO, Cn, NO2. These are the strong field ligands. So these ligands are having weak spin moment is there. These ligands are having weak spin. These are weak spin ligands. And another category is, the first category is strong field ligands. These are having weak spin. And the second one is weak field ligands. These are having high spin character. Strong field ligands are halide ions F minus, Cl minus, Br minus, I minus. These ligands are weak field ligands. These are the weak field ligands. These ligands are having high spin moment. These ligands are having high spin moment. These ligands are having high spin moment. Okay, students, what is the difference between strong field ligand and a weak field ligand? Generally, these ligands are known as strong field ligands. Why? What is the reason? These ligands are known as weak field ligands. Why? What is the reason? So these ligands are known as strong field ligands due to these ligands are donated electrons only one direction. These ligands are donated electrons in different directions. There is a difference. Okay, students, these ligands are donated electrons in only one direction, and these ligands are donated electrons in multiple directions. Okay, these ligands are donated only one side of the electron. That is, the type of ligands are known as strong field ligands. These ligands are donated electrons in multiple directions, that are known as weak field ligands. Okay, that are known as weak field ligands. These are the strong field ligands and these are known as weak field ligands. So for example, the splitting process of octahedral complexes are clearly observed. For example, in this complex, this is a central atom is iron, this is D block element. So this D block elements are containing 5 hybridized orbitals, 5 stationary state orbitals. So that stationary state orbitals are d orbitals, the central atom containing d orbitals that are dxy. Means I am going to discuss the splitting process of octahedral complexes. Splitting process of octahedral complexes. Splitting process of octahedral complexes. Students, so the octahedral complexes or tetrahedral complexes, any complex is taken. The central metal atom is a d orbital. The central metal atom is d orbital. D orbital containing d subshell containing 5 degenerate orbitals that are dxy, dyz, dzx, dx square minus y square and dz square. Okay, these are the 5 degenerate orbitals. So these degenerate orbitals submitted such amount of light radiation or such amount of energy. These are splitting into two ways. These are the splitting into two ways. So some of the orbitals are attained ground state and some of the orbitals are attained excited state. For example, dxy and dyz and dzx, these 3 orbitals are attained ground state level. So these orbitals are known as T2z orbitals. These are known as T2z orbitals. These are known as T2z orbitals. And next one, few orbitals are attained excited state. Only the T2z orbitals like dxy, dyz, dzx, these are attained ground state level. And a few orbitals like dx square minus y square, dz square, these 2 orbitals are attained excited level. These 2 orbitals are attained excited level. Okay, these 3 orbitals are attained ground state level. Okay, so these orbitals are known as easy orbitals. The excited state orbitals like dx square minus y square, dz square, these orbitals are known as easy orbitals. So dxy, dyz, dzx, these orbitals are known as T2z orbitals. So the middle portion of the energy barrier is indicated as delta naught. This is a energy barrier. Delta naught is indicated as energy barrier. Energy barrier. Okay, students. So these are the ground state orbitals. These are the excited state orbitals. In these energy barrier, in these 3 orbitals, is expressed minus 0.4 delta naught, minus 0.4 delta naught. So this energy barrier is expressed plus 0.6 delta naught. This energy gap value is expressed plus 0.6 delta naught. This energy barrier is expressed, the value is expressed minus 0.4 delta naught. Okay, students. So strong field ligands, for example, one of the complex is taken CO, NH3, 6 plus 3. This is an octahedral complex. Okay, students, see the example. This is a octahedral complex. This is one of the important octahedral complex and positively charged coordination sphere. So these ligands are observed. This is a strong field ligand. This coordination compound splitting process is observed. The first T2Z orbitals and EZ orbitals. T2Z orbitals are 3. These are degenerate orbitals, dxy, dyz and dzx. EZ orbitals are 2 orbitals are there. Okay, this is the strong field ligand, means weak spin. This is strong field ligand, means weak spin. So the spin moment is very weak. These electrons do not touches EZ orbitals, do not attain EZ level. Only these orbitals are paired T2Z orbitals. So okay, this is a 6 ligands are there, means 3, and the fourth electron is do not entered in this level. This is the excited level, this is a higher energetic level. So but these ligands are weak spin ligands. These are do not move excited state level. These orbitals, means these ligands are do not move excited level. Only the electrons are paid T2Z levels. So only the electrons are paid T2Z level. And the electrons are do not touches EZ level. So these electrons are do not touches EZ orbitals level. Okay, so this is a pairing order in this complex. This is a electron configuration. Okay, students, to calculate the crystal field splitting energy in this complex. Now, so many competition examinations, this concept is very important. So, the type of competitive examinations questions are observed in this topic. The type of questions are created to calculate the crystal field stabilization energy for the given coordination compound. To calculate the crystal field stabilization energy for the given coordination compound. Students, this is a strong field ligand, means weak spin complex. Only the 6 ligands are paired in these degenerate orbitals. This degenerate orbitals energy is observed minus 0.4 delta naught, means 6 electrons are there. 6 into, means our aim is to calculate crystal field stabilization energy. To calculate the crystal field stabilization energy. Okay, students. So the crystal field stabilization energy formula is T2Z. This is the octahedral complex. The T2Z level electrons, each electron energy is minus 0.4 delta naught. Means this is 6 electrons are there. 6 electrons into minus 0.4 plus EZ plus, means 0 electrons, 0 into this energy level is 0.6. Totally minus 2.4 plus 0. So finally 2.4 delta naught. The crystal field stabilization energy in this complex is minus 2.4 delta naught. Minus 2.4 delta naught. Okay, so this is a splitting process of octahedral complex, and at the same time to calculate the crystal field stabilization energy for the given coordination compound. Okay, once again recall in these points. Today I am going to discuss crystal field theory of the coordination compounds. Students, what is the importance of crystal field theory? Crystal field theory explains the colored property of the coordination compounds. Okay, now I am entered two different types of complexes like tetrahedral and octahedral complexes. Tetrahedral complex means the given coordination compound containing 4 ligands. That type of complexes are known as tetrahedral complexes. And the given coordination compound containing 6 ligands, that are known as octahedral complexes. Now students, so these ligands are subdivided into two categories. So one category is strong field ligand and another category is weak field ligand. What is the difference? My question is, what is the difference between strong field ligand and a weak field ligand? Strong field ligand means the ligands electrons are donated towards only one direction. That type of ligands are known as strong field ligands. So next one, the ligands electrons are donated towards multiple directions, that are known as weak field ligand. Strong field ligands are having weak spin. Weak field ligands are having high spin. Okay, now I am going to discuss splitting process of octahedral complexes. Now generally, the central metal atom is d block element in any coordination compound. The d block element containing 5 degenerate orbitals, that are dxy, dyz, dzx, dx square minus y square and dz square. So these elements, like this compound, react with such amount of heat. These d orbitals are degenerated. These d orbitals are splitted with different energy levels. So some of the d orbitals are attained ground state level, like that orbitals are known as T2z orbital, like that are known as dxy, dyz, dzx. And some of the orbitals are splitted to excited level, that orbitals are dx square minus y square, dz square. Okay, students, these degenerate orbitals, like ground state degenerate orbitals, energy levels are, so each electron containing minus 0.4 delta naught, and the excited state level, these electrons energy levels are each electron plus 0.6 delta naught. Anyhow, this is the splitting process of octahedral complex. And now our aim is to calculate the crystal field stabilization energy for the given coordination compound. Now, so the splitting process of electrons in a given coordination compound, this is a strong field ligand, means weak spin. The total electrons are dumped to T2z orbitals. T2z having 6 vacant electrons. This is octahedral complex. The total 6 valence electrons are dumped to these 3 orbitals. Okay, so T2z containing 6 electrons and EZ containing 0 electrons. Now the formula is to calculate the crystal field stabilization energy. That formula is, first one, crystal field stabilization energy minus 0.4 into T2z orbitals. So this is the formula for crystal field stabilization energy, minus 0.4 into T2z orbitals plus 0.6 into EZ orbitals. This is the formula to calculate the crystal field stabilization energy. Okay, now these number of electrons are substituted by using this formula. So this complex crystal field stabilization energy is minus 2.4 delta naught. This is the explanation for the splitting process, and to calculate the splitting process